Hello, ladies and gentlemen. This is kind of a good review of the prerequisite skills that are required for this unit. It's two concepts. One is laws of exponents. The other is going to be simplifying radicals. It is absolutely crucial to understand these concepts going through the rest of the chapter. So I'm going to make this video as quick as I can, so let's get busy. So first property, laws of exponents. All right. We know what exponents are. You have a base and you have an exponent, right? And that's usually a number. And that tells you that you're going to multiply that base by itself so many times. So there's several properties of these that we have to discuss. First is the product property, meaning if I multiply same bases, x to the m times x to the n, I notice my bases are the same. So what do I do with the exponents to simplify it as one term? I go ahead and I add them. Okay. Quotient property. All right. If I have x to the m divided by x to the n, I notice my bases are the same. So what do? I go ahead and I subtract the exponents. Power to a power property, meaning if I have x to the m and then I take this term and raise it to the n power, here is where I multiply the exponents. Okay. Product of a power property means if I have x times y all raised to the m power, then basically what I do is each factor inside here can get raised to that power. So we would get x to the m and y to the m. And just to let you know, you do, so if I have, say, x to the m, y to the m, and I raise this to the n power, I basically multiply the exponents here, and then I multiply the exponents here. Okay? Quotient of a power property is the same thing. If I have x to the m over y to the m, all raised to the n power, each term here gets raised to the n power, so it would be x to the m times n over y to the m times n. All right. The last one is negative exponents. Okay. And when you have negative exponents, if you have x to the negative m in the numerator, to make that exponent positive, we bring it to the denominator. And the same thing is if I have the negative exponent in the denominator, I bring that up to the numerator to make that exponent positive. Okay. So let's get to some examples using these properties. I'm going to state the property it's using. So here's the product property, right? If I look, I'm multiplying all the same bases, x, x, and x. So I write it as one single base x. And what am I going to do with the exponents? I am going to add them. So this would give me x to the 2 plus 5 is 7 plus 3. This is equivalent to x to the 10th power. Now, I used to like to tell kids I multiplied 2 x's here, I'd have 5 x's here, and I have 3 x's here. How many total x's am I multiplying? X to the 10th. So either way you look at it, it's the same thing. So example 2 is a quotient property, right? Right away, if I have same bases, I'm going to go ahead and subtract the exponents. So x to the 3 minus 2, y to the 4 minus 5, and then z to the 1 minus 4. Now what's tough here is 3 minus 2 is 1, 4 minus 5 is negative 1, then 1 minus 4 is going to give me z to the negative third. Right now, all of these are in the numerator. So I have to say, if it is a positive exponent, it stays. Negative exponent, it's got to go to the denominator. So x stays up here. Y comes down and make that exponent positive. Z comes down, make that exponent positive. And you are done. Okay? The other way I like to do it is here I can cancel out 2 x's. How many do I have left? Top. Here I have 4 y's, 5 y's. I can cancel out 4. How many do I have left on bottom? 1. Here I have 1z, 4z's. Cancel 1. I have 3 left on bottom. Example 3, power to a power. Write it as one base. Take the exponent to an exponent, and I multiply them to get x to the 6th power. Done. Here I'm doing product to a power, and at the same time, power to a power. So x to the 3 times 5, y to the 4 times 5, z to the 2 times 5. So x to the 15th, y to the 20th, z to the 10th. And we are done. Okay, next one, x to the 2nd to the 4th, right? Here, everything's going to get raised to the 4th power. So x to the 2 times 4 is 8. Y to the 3 times 4 is 12 over x to the 4th, y to the 8th. Now here, I have 8 x's on top, 4 on bottom. If I cancel them out, I have 4 left on top. Here I have 8 y's on bottom, cancel out 8 off the top. How many do I have left? Y to the 4th up top. And I am done. Then example 6, put that over 1, and I look to make that exponent positive. I bring it down. Then I keep the y to the 4th up top. Okay, so example 7, what I like to do is raise everything to the negative 3. So a to the 2 times negative 3 is negative 6. B to the negative 3 times negative 3 is 9. A to the negative 3. B to the negative 5 times negative 3 is 15. Then any exponent that's negative I'm going to make it positive. So this comes down, a to the 6th. This goes up, a to the 3rd. And I have b to the 9th, b to the 15th. So how many a's do I have on top? 3 on top, 6 on bottom. Cancel the 3 out. How many do I have left? 3 on bottom. Cancel off 9 off the top. How many do I have left on bottom? 6. And if I have nothing left on top, I have 1. All right, simplifying radicals. First thing you need is a list of perfect squares. And you can generate this list real easily. When we talk about a square root, you have the radical, all right, and inside we call it the radicand. And when we take the square root of it, we get the root. Now, we do have different indexes, right? So the number on the outside is called the index. And it basically tells us what to that power would give us the inside number. So when we just see square root, that index is 2. So what squared gives us this inside number, or the radicand? So right away, perfect squares. I take 2 and raise it to the 2nd power. I'm going to take my counting numbers, raise it to the 2nd power. So 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared, 81. 10 squared is 100. Then 11 squared is 121. 12 squared is 144. Okay, what you have to understand is what these translate to, right? Although we get square root of 4, that's equivalent to 2. This is equivalent to 3. It's equivalent to 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, perfect cubes, right? When we're dealing with cube roots, remember the index is 3. So now to make this list, we're going to raise each number to the 3rd power. Okay? So 2 to the 3rd is 8. 3 to the 3rd is 27. Then 6 to the 3rd is, sorry, why did I go 6? Sorry, 4 to the 3rd is 64. 5 to the 3rd is 125. 6 to the 3rd is 216. All right, we can keep going by just taking those counting numbers and raising it to the third power. Now, fourth roots, right? We're going to raise every counting number to the fourth power and the fifth roots and so on. So pause the video and I'm going to have all the roots on there and you're going to write them down. So here are all your fourth roots, here are all your fifth roots that you need to memorize. So all of them you see on here should be memorized. Now, every radical has its value, right? Such as when I see the square or the cube root of 8, I think of that as being 2. Cube root of 27 is 3. The fourth root of 16 is 2, because 2 to the fourth gives me 16. The fifth root of 32 is equivalent to 2. And we use these to help simplify radicals. Now, to simplify radicals, we find the largest perfect square that goes into the radicand. And we break it up into a product of two radicals, right? And then we simplify the radical if it can. Remember, if it's not a perfect square, we leave it inside the radical. So, root 8, right? What's the largest perfect square from this list that goes into 8? And when we talk about that, right, this part of it, find the largest perfect square that goes into a radicand. We're looking at the numbers, the radicands in each perfect square, right? These are what we're looking at. So which one from the largest perfect square goes into 8? And you should see 4 is that number. Okay, so we're going to break this up into square root of 4 times. What times 4 would give us 8? 2. Well, what's the square root of 4? 2. Can we take the square root of 2? No. So we leave it as is. At 32, there are two perfect squares that go into it, right? There's 4 and there's 16. What is the largest perfect square that goes into it? 16. So we're going to break this up into the square root of 16 times the square root of, what times 16 would give me 32? 2. Now, what is the square root of 16? 4 root 2. Okay. Next one. What's the largest perfect square that goes into 400? Yes, 4 is one, but it's not the largest, right? But even so, what do you notice about 400? Right? It is actually a perfect square itself, so it's 20. Okay? But what happens if you made the mistake of doing this? You would notice you get square root of 4 is 2 times square root of 100 is 10. What's 2 times 10? 20. All right? Example 4. Square root of 75. I'm going to break it up into what's the largest perfect square? 25 times what would give you 75? 3. Again, what does 25 simplify to? 5. Can we simplify root 3? No, so we leave it inside the radical. Okay? Now, the cube roots, the fourth roots, and the fifth roots are no different. Okay? What's the largest perfect cube that goes into 24? Well, I look at that list and I see 24 is divisible by 8. So I break it into the cube root of 8 times the cube root of 3, because 8 times 3 is 24. What is the cube root of 8? 2. I can't take the cube root of 3, so I write my answer like such. Okay? What's the largest perfect cube that goes into 54? Right? I look at that list, you have 8 doesn't, 27 does. Cube root of 27 times what times 27 will give me 54. Oh, sorry, 2. And what is the cube root of 27? 3 cube root 2. Now, 729, when I go up to that list, I'm looking at the fifth roots now, right? What's the only one that looks like it'll go into it? All right, and I will say it's 3, it is 243, okay? So 243 is the largest perfect fifth root. So the fifth root, 243 times the fifth root of 3, so that's going to be, it's going to be 3 times the fifth root of 3. If you write You are the best, Mr. Farina. On the top of your worksheet, I will give extra credit.